Hello, future engineers, viewers, subscribers, and students. There is another video. This is part 3 of beams by superposition method. So determine the external reactions at the supports by the superposition method. E is constant. So let's have the moment diagram by parts for each loading. Then the moment diagram by parts for the reactions. We moment center at D. Take note that for portion ABC, the moment of inertia is I, and for portion CD, 2I. So due to we divide this trapezoidal loading into two parts, uniform and triangular. So for the uniform load, 15 times 9 times 4.5 divided by 2, it is second degree. So that would be 303.75. Then for the triangular loading, 1/2 of 9 times 30 times 3 divided by 2, 202.5 kilograms. That's third degree. So we just imagine that EI is 1 in this case, although we already divided each value here by 2. Then for the 30 kilonewton load, 30 times 3 is 90. Then as it enters CD, because I is 2, 2 times the moment of inertia of ABC, so 90 divided by 245, and 30 times 12 is supposedly 360 divided by 2, so 180. So for this part, we imagine we have two loadings of 45 kilonewton meter couple and 180 minus 45 concentrated load with moment at the end of 135 kilonewton meter. Then for the 20 kilonewton, 20 2 at B is 40, but we do ignore this because it has no effect to deflections at B and C. So 40, 40 up to C, and as it enters CD, we divide it by 2, so 20 couple. Then finally, for the other effect, because we imagine there is 20 here, so 20 times 8 is 160. As it enters C to D, 160 divided by 280, and 20 times 17 is 20 times 17 is supposedly 340 divided by 2, so 170. So for the portion CD, due to the 20 effect of the 20 kilonewton load, we have a couple of 80 kilonewton meter and moment at the wall of 170 minus 80, so 90 kilonewton meter with this first degree curve. Then we also have for this portion 90 couple at this 90 moment at the wall at C. So let's evaluate EI delta C due to the load. And this is the moment diagram by parts due to the reaction. First, we have R sub C. R sub C times 9 divided by 2 is 4.5 R sub C. Then for RB, RB times 8, 8 RB. As it enters CD, divide by 2. So for RB, 8 times 17 is supposed to be 17 RB, but we divide it by 2, so 8.5 RB. So first EI delta C due to the reaction, so we only consider these moments at this wall. So it consists of moment 4.5 first degree. So EI delta C due to the load is 303.75 times 9 square divided by second degree plus 2 for the deflection at C. Then this one 202.5 times 9 square divided by third degree plus 2. For this next moment at the wall, imagine we have a 45 kilonewton meter couple and a couple which is at the wall due to this first degree curve, 0 degree couple, where for the first degree curve, the moment at the wall is 180 minus 45 or 135. So for the couple, due to deflection at C, 45 times 9 square over 0 plus 2. And for the 135 kilonewton meter couple times 9 square over first degree plus 2. Next, for this 20 couple, 20 kilonewton meter couple, so plus 20 times 9 square over 0 plus 2. And for this diagram, loading or moment, we have a couple 80 and 170 minus 80, 90 kilonewton meter couple first degree. So for the couple, 80 times 9 square over 0 plus 2. And for the 170 minus 80 or 90 kilonewton meter moment, first degree, so 90 times 9 square over 1 plus 2, which is that. So simplifying, combining AI delta C due to the load is 21,378.9375. And due to the reaction, due to this moment diagram, it is 4. EI delta C due to the reaction, 4.5 RC times 9 square over 1 plus 2. Um, Later, so let's solve first for the deflection at B here due to the load. So due to this moment diagrams of these loadings for portion BC, it was already calculated equal to that. So we will just add additional deflection at B due to the slope at C. So first, 8 times moment length 9 over second degree plus 1. Formula for the slope at C, then multiply it by 8 because the distance between B and C is 8. Then plus this one, 8 times 202.5 times 9 divided by third degree plus 1. Then for this diagram here, we have 45 and 180 minus 45, 45 couple. So for the couple, 8 times 45, 9 over 0 degree plus 1. Then for the 135 kilonewton meter couple, 8 times 135, length 9 divided by first degree plus 1. Then plus for this loading here at B, this is just deflection automatic. Moment 40, length 8, so 8 square divided by 0 plus 2, which is this. Then plus due to this loading, additional deflection at B due to the slope is 8 times moment 20, length 9 divided by 0 plus 1. Then due to this loading here, the effect at B would be deflection under the 30 kilonewton load plus deflection due to the slope at this point. So for the moment, 90 length 3, so 3 square, then first degree plus 2, which is this, then plus 5 times the theta at B, which at this point, which is 5 times moment 90 length 3 over first degree plus 1. Then plus for this loading here, slope only because we already evaluated the deflection in here. So for couple, 8 times 80, length 9 over 0 degree plus 1. Then for this first degree diagram, 170 minus 80 is 90. So 8 times 90 times 9 over first degree plus 1. And finally, for this loading, it is only due to deflection at B directly, and it is 160 times length 8 squared divided by first degree plus 2. This is deflection. Combining the EI delta B due to the load is 56,492.271. Then for the reaction, this is the moment diagram by parts for the reaction. So at C rather, EI delta C due to reaction is moment 4.5 RC length 9 square divided by first degree plus 2. So moment 4.5 RC length 9 square over first degree plus 2. Then for this loading here, we have couple and due to consider first degree curve, 8.5 RB minus 4 RB is 4.5 RB. So for the couple, 4.5 RB length 9 square over 0 degree plus 2. And for the first degree curve, 4.5 RB length 9 square over first degree plus 2. So that's it. We combined. It is EI delta C due to reaction at C is 121.5 R sub C plus 283.5 R sub B. So we can now set up the first equation, 121.5 RC plus 283.5 RB equals 21,378.93775. Call that equation 1. Next, for EI deltas B due to the reactions. So for this diagram, we just add additional deflection slope at B. And for this one, this is direct deflection at B. So since due to deflection at B, it is already calculated equal to this, we just add the additional deflection due to the reactions due to the slope for the slope at C. So EI delta B due to reaction is 121.5 RC plus 283.5 RB plus 8 times for this part, 8 times 4.5 RC length 9 divided by first degree plus 1. Then for the couple, plus 8 times 4 RB length 9 over 0 degree plus 1. And for this 4.5 RB times length, so 8 times 4.5 RB times length 9 first degree plus 1. Then for this part here, it is direct deflection at B. So 8RB 8 square over 1 plus 2. 8RB 8 square over 1 plus 2. That's deflection due to this moment at the wall at C. So combining and simplifying and equating to 56,492.271, we have 283.5 RC plus 5425 over 6 RB equals 56,492.271. Call that equation 2. Solving equations 1 and 2 simultaneously, we get R sub C 112.419 kilonewtons and R sub B 27.231 kilonewtons. Then let's apply it there. Then summation versus y equals 0. Then you check that R dy is, of course, dx is 0, dy is equal to 180.35 kilonewtons. Summation moment about B equals 0. MD plus 15 times 9 times 4.5 plus 1 half of 9 times 45 times 3 plus 30 times 12 plus 20 times 19 minus or equals to 7.231 times 17 plus 112.419 times 9 and show that moment at D is equal to negative 277.802 kilonewton meter. So that's it for this video.